We're working on some stuff here out of Unit 7-8, Box E. We're going to look at the intersection of three planes today. And before we even start looking at three planes, we're just going to talk a little bit about what it means for there to be a solution to a system of three planes. So if you have three planes, in order for there to be a solution to the system, there has to be at least one point that is common to all three of our planes. Okay? And we're going to use this terminology to discuss the various possibilities when we have three planes in space. If there is no solution, so there's no point common to all three of the planes, we're going to say that the system is inconsistent. Okay? And if, conversely, if there is at least one solution, we're going to say that the system is consistent, i.e. that a solution exists. Now, if we have at least one solution, then we're going to talk about how many solutions we have. We're going to say that this system is consistent and independent if it has only one unique solution, so our three planes intersect at a single point. Or we're going to say that it's consistent and dependent if instead of one single solution, we have infinitely many solutions. And there are two possibilities here. We can have infinitely many solutions if our intersection is a line or our intersection is a plane. Whereas if it's independent, one unique solution is going to intersect in a point. Okay. So if our intersection is a line or a plane, obviously we have infinitely many points on a line and infinitely many points on a plane, so we have an infinite number of solutions. And this will become a little bit more clear as we look at the possibilities. And that's the first thing that we're going to do here. We did this when we were looking at every kind of intersection. We said, okay, if we've got these two systems in space, what are the possibilities for how they intersect? When it was lines, we said they could intersect at a point, they could intersect, they could be skew lines, they could be parallel and distinct or parallel and coincident. When we have three planes, we have 8 possibilities here. So let's take a look at how we can sort of organize these possibilities. Sort of the first group of possibilities occur when all three of our planes are parallel to one another. And the way we can check to see if all three of them are parallel is we take a look at the normals of the planes. So if all three of the normals are scalar multiples, all three of the planes will be parallel. Now, in here we have 3 possibilities. All of the planes could be parallel and distinct, and that's what I've kind of tried to draw over here. We've got our 3 planes, plane 1, plane 2, plane 3, 3 separate planes, parallel and distinct. Now, if our planes are parallel and distinct, is our system going to be consistent or inconsistent? Well, if they're parallel and distinct, we can't have any points that are on all 3 of them, so we can't have a solution. So this has to be always inconsistent. Okay. So if you're working away on a problem and you find that all 3 of the planes are parallel and distinct, you can say that the system is inconsistent, the planes are all parallel and distinct. Next possibility, we could have 2 of these planes being coincident, and then the third one is off on its own. It's parallel and distinct. Again, this system is going to be inconsistent. Because we don't have a single point that is on all 3 of these planes. Third possibility is that all 3 of our planes could be one on top of each other. All 3 of them could be coincident. Now, in this case, is the system going to be consistent or inconsistent? What do we think? Absolutely. Because we are definitely going to have, if all three planes are basically the same, then any point that is on one plane is automatically going to be on the other 2 planes. So our system is going to be consistent here. Now, if it is consistent, is it independent or dependent? Well, are we going to have one solution or are we going to have infinite solutions? Well, if our intersection here is a plane, because the planes are all exactly the same, any point that is on any of these planes is going to be on the other two. So we're going to have an infinite number of solutions. So it is going to be dependent. And by dependent, we just mean that the exact solution that we choose depends on the value of the parameter that we pick. So we could pick a particular value of t and s on this plane to get a single solution. So these are our first three possibilities, if all of our planes are parallel. We have another set of possibilities that occur if two of our planes are parallel and the third one is not. Okay? And we have two possibilities in this case. Okay? So we check our normals. We find that two of them are scalar multiples. We can have two of our planes here are parallel and distinct that you see right here, and this third one kind of intersects both of them. So what we're going to have in that case are two lines of intersection. One kind of going like this, and one kind of going like that. Okay. Is this system going to be consistent or inconsistent? What do we think? What do you think, Richard? It's going to be inconsistent. Okay? You can have a point that is on both this plane and this plane. You can have a point that is on both this plane and this plane. But because these two are parallel and distinct, they're going to have no points in common. So there can't be a point that is on all three of these planes. Okay? So this system is going to be inconsistent. The other possibility in this section is we can have two planes that are coincident, that are essentially the same plane, as we've shown here, one inside the other. And the third one comes along and intersects both of them. So in this case, we're going to have a single line of intersection. I sort of draw that in here. Now, in this case, is this going to be consistent or inconsistent? Do we have any points that are on all three of these planes? What do you say, Brody? Mm-hmm. Any point on that single line of intersection is going to be a solution. So it's going to be consistent, and we have an extra ent in there that we don't really need, so just consistent. And because there's an infinite number of points on that line of intersection, it's going to be consistent, and I've still spelled consistent wrong. And I'm still spelling it wrong. Consistent, and it's going to be, again, dependent. Okay. Now, the trickiest ones occur when none of our planes are parallel. So none of our normals are parallel to one another. We have three possibilities here as well, and I've illustrated all three of them. We can have all three of these planes intersect in a single line. So they form kind of this nice little star pattern right here, and our line of intersection comes along like this. Check our normals, we'll find that none of our normals are parallel, but what we can check to see is whether our normals are coplanar in this case. Because if we look at, I'm not sure how I can draw this here, but if let's say we look at the normal of this plane right here, it might come off like this. The normal to this plane here might sort of come down like this. The normal to the third one might sort of come out like that. All three of these normals are going to be in the same plane. You can imagine a plane that is sort of perpendicular to all three of those. It's going to contain all of our normals. N1, N2, and N3. Okay? So in this situation, the normals are going to be coplanar. So that gives us a little bit of information about the system. Now, if all three of them intersect in the same line, obviously that line is going to be our solution. So the system is going to be consistent and dependent. Seventh possibility, we can have our three planes intersecting. Plane 1 can intersect plane 2 can intersect plane 3 can intersect plane 1 again, but there isn't a common intersection. Instead, what we have are 3 lines of intersection here, here, and here. Okay. Just like the situation above it, the normals will still be coplanar, but this time our system is inconsistent because we don't have a single, we have these 3 lines of intersection, so there isn't going to be a point that is common to all 3 of these lines. And the final case is if all 3 of our lines, all 3 of our planes, sorry, can intersect at a single point. So you can see the situation illustrated there. We've got 2 of them intersecting and the third one sort of at a different angle here. So in this case, none of our normals are parallel and the normals are not coplanar. So we get intersection at a single point here. So if this all intersects at a single point, we get a system that is consistent. This is the only case where our solution is independent. Okay? So another way of saying that the solution is independent is that we get a unique x, y, and z. Okay? We'll get single values of x, y, and z that satisfy all 3 of these equations, and nothing we do can change what those x, y, and z values are. So these are the 8 possibilities. So we're going to proceed here. The way to approach these kinds of questions, I think, is to start with by looking at the normals, look at the information that the normals tell you, and then try to figure out which of these situations you're looking at and adjust your solution accordingly. Okay? So these questions, they tend to take a lot of time and a lot of writing. And the way to get good at it is to try to do as many as you can, and then you'll sort of see how the solution is going to work as you go through it. Okay? So I'll try to lay out a system here, or a set of steps that you can use to try to approach these questions. So here's a sample question that you might have here. Determine the intersection of these 3 planes. Okay? And when they say determine the intersection, what they want you to be able to say is it consistent or inconsistent? If it is consistent, is it dependent or independent? If it is independent, state the coordinates of the point of intersection. If it is dependent, state the equation of the line of intersection, and so on and so on. And if it is inconsistent, you want to sort of say how you know it's inconsistent. Okay? So let's label these things plane 1, plane 2, and plane 3 here. And first thing we want to do is we want to take a look at the normals. So I'm just going to say check the normals. Because we're checking for 2 things when we look at the normals here. Number 1, we want to see if these things are parallel. And number 2, we want to look to see if they're coplanar. So let's just write out our normals here. For plane 1, our normal is 1, 2, 1. For plane 2, our normal is 2, negative 1, 1. And for plane 3, our normal is 3, 1, negative 2. And the first question we're going to ask ourselves is, are any of these planes parallel to one another? And we check this by looking at the normals. So looking at these 3 normals, is anything parallel here? Are any of these normals scalar multiples? Richard's shaking his head because, yeah, none are parallel. So already we know that we have 3 possibilities. They intersect in a point, they intersect in a line, or we have that situation where they form that little triangular prism in the middle. And we want to try to figure out which of these 3 we have. The next thing to check is, are they coplanar? Okay. Now the easiest way to check that is to do the triple scalar product. Do n1, do the cross product with n2, and then do the dot product with n3. Now you've all done the triple scalar product about a few hundred times here, so I'll just let you know that the answer we get here is 20. So what does that tell us if our answer is 20? Are these things coplanar or not coplanar? Again, Richard's shaking his head. Yeah. If this was 0, they would be coplanar, but it's not 0, so these things are not coplanar. So now we've narrowed this down to one situation here. We know we have option 8. These things are going to intersect at a single point. So we want to find this point of intersection. So we'll just say find point of intersection. Okay, and we're going to proceed in a similar fashion to what we did when we had two planes and we were trying to do the intersection. Our second step here is we're going to eliminate, we're going to pick two of these equations, two of these planes, and eliminate one variable. So let's just say eliminate one variable from two of the equations. And the two equations that we pick are kind of, well, we're going to pick the ones that are easiest to work with. So I think the easiest one to do here is going to be eliminate y from plane 2 and plane 3, because it's already set up nicely to do elimination. So we're going to eliminate y from plane 2 and plane 3. Okay. And we're going to do this just by adding equation 2 and equation 3 together. So rather than write that all out again, let's just say we'll do plane 2 plus plane 3. And what is that going to get us? Well, let's see. 2x plus 3x gets us 5x. Negative y plus y eliminates y, which is good. Z minus 2z is negative z. And all of this is going to equal 5 plus 1 gives us 6. So we've eliminated y from planes 2 and 3. Let's call this equation 4. Okay? Because we've got plane 1, plane 2, plane 3. Our original equations, we'll call this 4. So we used 2 and 3. We eliminated y. Our next step is we're going to pick another pair of equations and eliminate y from them. So eliminate y from, let's just say, another pair of equations. So we don't want to use 2 and 3 again, but what we could use are, we could do 1 and 3. If we multiply 3 by 2, oh wait, we could do 1 and 2. That would be even easier because they have opposite signs already. So what we're going to do here is we're going to do just equation 1, plane 1, times, and we're going to add to it 2 times plane 2. So let's write this out here. We've got to have plane 1, which is going to be x plus 2y plus z equals 12. And we're going to then work with 2 times plane 2, which is going to be 4x minus 2y plus 2z equals 10. Okay. And then we can add these two. So we got plane 1 plus 2 times plane 2. Let's add these up. What we're going to get here is 5x plus 3z equals 22. Let's call this equation 5. So if we look at equation 4 and equation 5, we now have two equations with just two unknowns, x and z. So we can use 4 and 5 to solve for the values of x and z. So that's going to be step 4 here. Use 4 and 5 to solve for x and z. Now let's look at these two equations here. This is going to be, let's see, it's going to be relatively easy because we just need to subtract those two equations because they both have 5x. So we can eliminate that 5x pretty easily from both of these. So we'll just write this out here. We've got 5x minus z equals 6. Equation 5 is 5x plus 3z equals 22. And we're just going to subtract these two from each other, which is going to get us negative 4z is 16 minus 22 is negative 16, which tells us that z is going to equal 4. Now, if z equals 4, let's sub this back into equation number 4, and we'll get 5x minus 4 equals 6. So 5x is going to equal 10, and x equals 2. So now we know our value for z, we know our value for x. All that's missing is our value for y. So how do you think we can find our value for y here, now that we know x and z? This is going to be step 5. Yeah. What are we going to plug them into? Yeah. Find y from 1, 2, or 3. Okay, we've got x and z. Let's just plug everything in here. So I'm going to use equation 1, which was x plus 2y plus z equals 12. And we sub in x is 2, z is 4, which tells us that 2y is going to be 6, or y is 3. And we're done. We've got x, y, and z. So we can say, therefore, we can say the system is consistent. And I'll take another stab at writing consistent here. Consistent. And because we have a single unique solution, it is independent. And the solution is that point that we just found, x, y, z. So x was 2, y was 3, and z was 4. So our solution is the point 2, 3, 4.